They say that only God can create something out of nothing. But here we are talking about physics. So let's just say that 90% of the universe is missing, or rather, invisible. We can't see most of the stuff the universe is made of. And I'm not talking about dark energy, which is basically a property of space itself. No, I'm talking about dark matter, which is a type of matter that makes up a whopping 80% of all matter in the universe. And yet, we can't see it. We have never directly detected it. All we have are some indirect observations and a lot of theories. So how did we even find out that there was something invisible holding the universe together? Well, it started with a simple observation of galaxies. They rotate. Stars at the edge of a spiral galaxy rotate around the center, just like our Earth goes around the sun. But there's one key difference. Stars and galaxies rotate much faster than they should. It's as if our solar system had a giant, invisible, massive bowling ball in the middle, pulling the planets around it. But there isn't any such thing in the center of this galaxy. There shouldn't be anything at all because we can actually see through the galaxy. And what we see in the center is just empty space? Or is it? This unexpected discovery was made by Fritz Zwicky in the 1930s when he was studying the Coma Cluster, a group of galaxies 270 million light years away from us. Zwicky found that the galaxies within the cluster were moving much faster than expected. It was as if there was a lot more mass in the cluster than he could actually see. He called this missing mass dark matter. But hold on a second, if these galaxies were moving faster than expected, wouldn't that mean that they're not actually rotating at all? Like maybe they're not even spinning. Maybe they look like they're rotating, but they're really just flying through space in a random direction. Well, no, that's not the case. We have a way to tell whether an object rotates or not, and that is by looking at how it bends light. This effect is called gravitational lensing, and it happens because mass warps space, and since light always travels in a straight line, it gets bent by those distortions. Basically, if you know how much space-time is warped, you can tell exactly how much mass is around. And in the case of galaxies, we have been able to map the distribution of mass in them by measuring how much they bend light from objects that lie behind them. And what we found is that the majority of the mass in galaxies is in fact, in this invisible form, the dark matter. So, now, it was pretty much confirmed that there was this invisible stuff out there. But what exactly is it? Well, the most popular theory is that it's some type of particle. Something that's similar to the particles we can see, but with some key differences. For example, it doesn't interact with the electromagnetic force. That's why we can't see it. Otherwise, it would emit or absorb light. It also doesn't seem to interact with itself, which rules out a lot of particle physics models. This particular type of dark matter is called cold, because if these particles were moving very fast, they would have probably smashed into each other long ago. A good candidate for this type of dark matter is the hypothetical axion, a particle that has been theorized to explain some problems with the strong nuclear force. Axions would interact with visible matter, but only through gravity. And we don't know exactly how heavy they are, but it seems that they would clump up in large quantities in the center of galaxies. So that would explain the extra mass that we see. But axions aren't the only type of dark matter out there. There are a lot of other particles that have been theorized, and some of them are even considered warm or hot, meaning that they're moving so fast that they would not clump up into large objects. In fact, this is one of the reasons why we haven't found dark matter yet. If it's some type of heavy particle, then it's probably hiding in places where a lot of matter normally hides. In stars and planets and black holes. That's why finding dark matter would be such a big deal, because it would tell us that there is some new type of matter out there. And finding new types of matter is usually the precursor to a new physics revolution. You see, everything we know is made of atoms, protons, neutrons, and electrons. And the standard model of particle physics says that these are fundamental, that they're as simple as they can possibly be. But if we find dark matter, it would tell us that there is some type of matter that we're missing, some more fundamental particle. Unfortunately, though, we still haven't found it, but we're working on it. There are several experiments out there looking for dark matter right now, such as the XENON1T experiment in Italy, which uses a huge tank of liquid xenon to look for dark matter particles smashing into the xenon atoms. If they find anything, it will be huge news. But if they don't find anything, it just means that we need to come up with some new ideas. Maybe dark matter isn't made of particles at all. Maybe it's some type of exotic matter, like a lot of negative energy density, for example, which would require a modification to Einstein's general relativity. At the end of the day, we still don't know what most of the universe is made of. Yes, we can measure its effects, but we can't see it, and we may never be able to. The universe is mostly invisible to us, and we barely understand it. But the more we learn, the more we realize how little we know. And that's what makes science so exciting. If you want to learn more about the amazing science that happens behind the scenes of this show, it's a great way to support us. And you get access to some pretty cool perks, like, for example, a weekly podcast where you can hear more about the making of this show and the science behind the stories we tell, or the particle accelerator in your living room. Thanks for watching. See you next time.